Hello, my name is Prasanna Rangasamy. This talk is about selective event processing for energy efficient mobile gaming, published in IASWC 2020. This was done in collaboration with my advisors and colleagues from Penn State. We played a variety of games on a smartphone, like those with very simple flow such as Color Fun or Memory Game, and arcade games such as Candy Crush, Green Wall, and an AR game called Chase Wisply, and high intensity graphics and compute games such as Angry Birds Evolution and Race Kings. When we plot the hours it takes to drain a 100% charged battery by playing these games, we observe that with an idle phone where we do nothing but wait for the 100% charged battery to be drained, we observe that the battery drain happens in about 20 hours. But even with the simplest of games such as Color Fun or Memory Game, where the user just have to touch the lightest of the two colors when displayed, the battery drains in just 7 hours. And as the complexity of gaming increases, we observe that the battery only lasts for lesser and lesser time, and with the most complex game, Race Kings, we observe that the battery lasts only about 2 hours for playing with a 100% charged battery. This shows that even with a very good battery charge, we can only play anywhere from 2 to 7 hours of gaming in a smartphone today. To optimize for this rampant battery drain problem, we observe that a typical game execution spends about 30% of its event processing in wasteful, redundant, and avoidable computations. As this example shows, the user may swipe up with a variety of input options such as here, 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 etc. But these are all swipe ups for the game and has the same effect, which is the output. Since these swipe ups happen at different XY coordinates, the input processing still happens and is considered as two different inputs. This can potentially be avoided when we know the domain that this input is going to be used for, and consequently the battery drain can be slowed down and not necessarily be as rampant as we observed. We next explore the possibility of building a lookup table with the union of all possible input-output fields we see during the execution and plot the lookup table size in GB versus the percentage of execution that gets covered with the lookup table. As seen, a typical smartphone has 6 to 8 GB of DRAM and anywhere from 64 GB to 128 or 256 GB of SD card capacity. And what we observe is even for less than 5% of the execution, we exceed the total DRAM capacity, and for storing of execution of 40%, we have to have 64 GB of lookup table space. This is definitely not the right way to short circuit executions, so we need a better way to short circuit redundant event processing. To avoid such large lookup tables, we feed the lookup table input-output fields to a ML algorithm called permutation feature importance in these prior works. And what it does is it takes the input fields and sees which input fields are going to be important and which are not, and keeps removing a combination of them till the error and report the error percentage. For example, in this chart, the input size is around 1 MB, and PFI keeps removing unimportant input fields from the table till we get to a point where removing any more input fields is going to cause too much error in the output we generate. So with this tunable ML, we reduce the lookup table size by 2 to 2% of the original size, and when we use this lookup table to short circuit the execution, we save around 32% in terms of energy. Thank you for listening. Please read the paper for more details.